using an elliptic curve. So now I have to choose what kind of elliptic curve I want to use. Two kind of common families of choices are Weierstrass curves or Edwards curves. So Weierstrass curves like Sec-P256 or the NIST curves. P256K1 is used in Bitcoin. And then there's Edwards curves like curve 25509 or 4Q. And the first property is that if you want a prime order group, then you can't quite get that with an Edwards curve. You're going to have a small cofactor, so you'll have like a group of order, say like 4 times a prime or 8 times a prime or something. So that seems kind of bad because it's not really what we wanted. But if we look further, you know, Edwards curves have faster formulas, so that sounds pretty nice. Those formulas are also complete, so they work with all of every possible inputs. Will always compute a correct result. You don't have to do any special cases. These also exist for Weierstrass curves, but those formulas which were published in the last few years end up being about 50% slower, so that's like kind of sad, so I put a sad face, although it is, you know, technically there. And so because of these complete formulas, it's pretty easy to implement Edwards curves in constant time, whereas if you do that with a Weierstrass curve, it's like more work. So like having the simple thing be the easy thing, be the correct thing is pretty nice. So you might ask like, okay, well, you know, it's only going to be this like small conceptual mismatch where we wanted a prime order group and instead we got this like other thing, there's like an extra factor of 4 or 8 or something. So like what could possibly go wrong? Well, so the big problem, like fundamentally, is that your security analysis for some abstract protocol, which some person has written down generically, does not actually apply to whatever concrete implementation you have. So if you've got the like latest, coolest proof system and you're like looking at the security analysis and then you try to implement it and you don't use a prime order group, then like whatever security analysis they did doesn't really matter because it doesn't actually apply to your implementation. If you do full validation that all of your points are all in the correct subgroups, that usually requires multiplying by the curve order, which is quite expensive. So that negates any speed up that you might have hoped to get. And so then you can say, okay, well, I'll just do some kind of like ad hoc tweak, right? Like I will multiply by 8 or 4 in this place and then like do something else in this other place and like slightly tweak it. And like maybe that will work, but now that's like very specific to the protocol that you have, and you have to kind of redo the security analysis or maybe just prove that all your tweaks actually do what you want them to do. And suppose you do all that correctly, you can get these cool like subtle features that come out of this. So for example, in ED 25519, you can have like totally standards conformant implementations that are not required to agree on whether or not some given signature is actually valid. You can have different behavior between single and batch verification, where you can have a signature that could verify under batch verification, but not when it's verified standalone. So that's like very cool if you have applications involving consensus. And also because the protocol has these tweaks to try to improve security, those are incompatible with like the normal way to do hierarchical key derivation. So now if you want that feature then becomes even more complicated. And that's in the best case, right? In the unhappy case, you don't do the tweak correctly and you have a catastrophic failure and your whole thing is totally insecure. Okay, so that would be bad. So how do we fix this like problem? The answer is using decaf or ristretto. So now I'm going to tell you what those are, and then try to give you a little bit of insight into how they work. So this is a construction by Mike Hamburg of a prime order group. It uses a non-prime order curve internally, and it just forwards all the group operations into that curve, so there's no overhead to do any group operations. And you get this canonical, non-malleable encoding of elements of a prime order group. What I mean by canonical is that every group element has a canonical bit string, which is its encoding, and the decoding function will reject any bit string that isn't the canonical encoding of some group element. And it's kind of nice because it's like batteries included, so it like has all this functionality that you're going to need. So it comes with a single hash to group method. So if you want to do like a VRF or you want to construct some orthogonal generators, you don't have to like figure out like how you're going to do that. It's all just sort of built in. So that's pretty nice. And now I'm going to tell you a little bit about how it works. To do that, I have to tell you about some various different curve shapes and stuff that we're then going to combine to explain how this construction works. The first one is Montgomery curves. So they have this shape, two parameters, B and A. B is like a twisting parameter, and A is doing all the work. So up to isomorphism, there's actually like only two choices of B. These are pretty well known because they have this fast sort of pseudo multiplication, where if you know the V coordinate of some curve point, then it's very easy and efficient to compute the V coordinate of its of some scalar multiplication. So if you want to do like Diffie-Hellman, that's pretty cool. This doesn't actually work on the curve exactly, but I don't want to get into that at the moment. The other thing that is quite nice about these that will appear later in the talk is Dara has noticed that if you do the full group operation on a Montgomery curve inside of a circuit, you can do that very efficiently with quite few constraints. So that's nice. The second kind of curve that we're going to use are Edwards curves. So they have this shape with two parameters, A and D. Again, the D parameter is doing most of the work, and the A parameter is this sort of twisting factor. And why do we care about these? First, they're things to know. They're birationally equivalent to Montgomery curves. So if that doesn't mean anything, it's sort of like isomorphic, except on a finite set of points. And they're nice because they have the fastest known formulas for curve operations, which was published in 2008 by Hasil, Wong, Carter, and Dawson. And that paper also analyzed the idea of what if you could do a single curve operation over multiple processors, which is somewhat impractical, but actually it turns out that you can do that parallelism using vector instructions. So you can have like vectorization inside of the curve operation, which makes it actually even faster. And the third one that we're going to be using in this construction are these Jacobi quartic curves. They have this shape. It's a degree 4 equation, and it has two parameters, E and A. Why would we care about these? Well, the reason is that the two torsion, which is all of the points where if you double them, you get the identity, or if you multiply by 2, you get 0. That two torsion for this curve is very easy to write down. And we can write it explicitly in the following way. We can say if we have a point S and T, what are all the points that are S and T plus some small point of small order? And that has a very nice compact description that doesn't seem quite meaningful yet, but what we're going to show you is that you can use this to define an encoding on that Jacobi quartic. So suppose that I have this thing where I say, I've got a point up to 2 torsion, and I want to find a canonical encoding of it. Well, if you have two sign choices, that determines one of these 4 points, right? So if I choose, say, like I want S to have to be non-negative, then that will select between the first and the second, as well as between the third and the fourth. Then by making a second sign choice, like the sign of T over S or S over T or whatever, you can choose between the remaining two candidates. So if you get two sign choices, you get a canonical representative of this set. That representative is going to be determined by its S coordinate. So now you can efficiently encode a point on the Jacobi quartic up to 2 torsion just by determining a canonical representative with two sign choices, and then using the canonical encoding of some field element as the encoding of that point. So that's, a very nice little observation from the decaf paper. But again, it's not really clear how this helps because we don't actually really want to use this curve, right? So the next piece of this construction is linking up curves with isogenies. So if you don't know what an isogeny is, it's basically a map between curves that respects the group structure. And a cool thing about isogenies is that whenever you have an isogeny, there's a dual isogeny in the opposite direction. So you can draw these as a graph, and you can actually draw sort of this family of curves that are related by isogenies. Starting in the top left, there's some Edwards curve with parameters A and D, and we'll have those be kind of like the root of all these. All these curves have related parameters, so we'll fix those as the initial variables, and then write everything in terms of those. That Edwards curve is connected to this Jacobi quartic in the center, with parameters a squared, a minus 2d. It's also isogenious to this other Edwards curve in the top right, which has the flipped a. And it's also isogenious to this Montgomery curve at the bottom. And there's this dashed line, which is denoting that Montgomery curve is birationally equivalent to a third Edwards curve with some other parameters whose relation I didn't write in the slide, but that's a connection that's there. So now we know, okay, we can do some encoding on this Jacobi quartic, and we know that there's these mathematical relationships between this Jacobi quartic and these other curves. So can we combine all these ingredients? And the answer is yes. You can use these isogenies to transport the encoding along this to wherever you want on this isogeny graph. And the reason that works is because of the following observation. So if we have some group homomorphism, phi from G to H, and we have G prime, which is a normal subgroup of G, and there's a third condition that I forgot to put on the slides, but then the slides are immutable, so it's missing. Which is that the kernel of phi has to be contained in G prime, then we get this induced map on the quotient groups. So we can get a map that goes from G mod G prime to phi of G mod phi of G prime, and that's going to sit inside of H mod phi of G prime. Why is that useful? Well, so for example, if phi is one of the isogenies from that graph, suppose it's the one that transports you from the Jacobi quartic to the Edwards curve, then we know that J mod J2 is going to be isomorphic to phi of J mod phi of J2, and it turns out that that's going to be isomorphic to 2E, which is all of the points on E that are doubles of some other point, mod that curve's 2 torsion. And now if E, the point is that this isomorphism is going to transport the encoding. So if none of that sort of quotient group facts actually made any sense, the kind of structural thing of how these pieces fit together is that the isogeny is going to induce an isomorphism of quotient groups that we can use to transport the encoding from the Jacobi quartic to some other curve on that graph. And actually, it doesn't have to be the Edwards one, it could be any of them. And now if we notice that, if E has cofactor 4, then we're actually already done, right? Because 2E, E is going to have order, say, 4 times Q. So all the doubles of points, well, there will be 2 times Q of those. And when we mod out by the 2 torsion, that takes out another factor of 2, and so we get a prime order group. In the cofactor 8 case, there's an extra step that is described on the website and not in this talk. And so how does this kind of fit together with decaf and ristretto? Well, if we draw that diagram that we had before, right? We've got an encoding that's defined on this Jacobi quartic in the center, and then there's all these other related curves. So decaf transports the encoding from the Jacobi quartic in the center to the Edwards curve in the top left. And this works really well with the curve ED448 that Mike made, where that curve is defined as a small d Edwards curve. However, if you wanted to use this with curve 25519, then that curve was originally defined as a Montgomery curve, and then ED25519 is the birationally equivalent Edwards curve. And so where that fits in this diagram is on the bottom row, right? So the Montgomery form of curve 25519 is going to be in the place of that M, and the ED25519 curve that has a large d is over in the bottom right corner. And so what ristretto does is you transport the encoding from the Jacobi quartic to the Edwards curve that you're going to use internally via this Montgomery curve. But actually, either of these schemes can use any of these isogenous curves that they want internally, which means that if you have ristretto that's using curve 25519, it's actually not required to use that curve internally. You could use like a different curve with like smaller parameters that might be faster, and it's still like totally wire compatible, which is pretty cool. And that construction is actually called ristretto 255. So this is a ristretto parameterization that uses curve 25519 internally. It's implemented in Rust in curve 25519 Dalek, which is a library that I wrote with Isis Lovecraft. Using this like vectorized parallel formulas strategy that I mentioned a little while ago, you can actually have this be up to 4 times faster than SecP, which is pretty cool, under like, you know, the most favorable benchmark comparison thing. And there's other implementations. There's C and libsodium. There's a Go implementation that I worked on with George Tankersley and Filippo Valsorda. There's a Java implementation that Strad from the Elliptic Curve company wrote. And there's an internet draft that specifies everything. So if you know, this whole construction with this all like isogeny graph and everything, you know, that's the sort of conceptual level of how this works, but when you actually implement it, it's just like a bunch of formulas, and those are all in this internet draft. And so I'm just going to close out with some vague ideas about using decaf in the circuits. So everything that I described at the beginning of the talk about like why you might want to have this construction, I think applies equally well to people who want to do curve operations inside of a circuit, because when you have a correct abstraction, right, you're going to have like well-factored pieces of your circuit code, and I think that's pretty important because it's already very complex and difficult. So it would be cool to have either decaf or ristretto inside of circuits. And so there's some notes on that on this website, doppio.group, which is, yeah?
Also see ticket 4024 on the
Yes. So that website is some project that I started working on with Kathy Yun. But it's aiming to do like a prime order group inside of a ristretto bulletproof. But it builds on Sean and in particular Dara's work on JubJub. Actually, Dara has done an analysis of trying to do ristretto for JubJub, which ends up being like not super favorable because every time you do a sign check inside of a circuit, that's quite expensive because you have to encode the field element into bits and then do a bunch of bit constraints. Dara has like an amazing set of notes on that. But in general, I think that there's actually some opportunities to do a little bit better. Like for instance, if you have a proof system where the embedded field is 3 mod 4, then you could maybe get like an algebraic definition of negativity, and then all the sign checks would become free and stuff. But I think a thing that's pretty cool is that using this construction, you know, the actual internal curve that's used to implement the group is a complete implementation detail. So 2 implementations can use different curve models, and they'll be perfectly wire compatible, even if they, you know, for all functionality, including like hash to group and everything. And the reason that this is interesting for the circuit use case is that if you're in this sort of software cost model where like you're actually executing software and you're trying to perform these group operations, then you could use like one curve model that will be very efficient for software. But then if you're in this like circuit world where you're actually certifying computation for a zero knowledge proof, you could use a different curve model that would have fewer constraints, like the Montgomery formulas that Dara has. And that is a complete implementation detail. So there's a lot more flexibility for optimization internally by having a sort of more minimal interface externally. So that's it. Any questions? Cool. Oh.
Yes, we heard that Starks are post-quantum out of the box. And now I see you care for isogenies, and I know that signature schemes based on isogenies might be a good candidate. Do you think about this? Because it is some sort of a bad smell, to my knowledge, that snarks still use pairings with elliptic curves, right? So what do you think of that? Is this something you care for, or is this out of the...
So the isogeny constructions that you would use to provide like a post-quantum secure primitive use isogenies in like a sort of completely different way. In this setting, the isogenies are just used as part of this construction. And so there's no post-quantum security whatsoever. So if there's, the security of this construction is exactly the same as the security of the underlying curve, so it's not post-quantum secure. But it doesn't really matter if there's like a future quantum computer if you like screw up multiplying by the cofactor today, because then you're just, done. So, yeah.
Okay. First of all, I love decaf and ristretto and what they're trying to do. There's a different way of sort of achieving a prime group abstraction, which is just to use the subgroup and do all of the subgroup checks. And in the circuit, it turns out that if you do that, then the encoding is 1/3 the cost of ristretto, and the decoding is half the cost. So, but you don't get the interoperability with using ristretto outside the circuit. So which do you think is more important? Having the more efficient circuit operations or being interoperable with ristretto encoding?
I'm not sure. I think that, I guess it depends how it's kind of encapsulated. If you can, I don't know that like it's going to be...
I mean, I'm oversimplifying the cost slightly because you still need to do the subgroup check to generate the witness, but that's cheap.
So I think that the issue is that like the speedups that you get outside of the circuit are maybe it depends basically on like how much you care about performance of group operations outside of the circuit. Right. So if you're only ever using this embedded curve in order to like do operations in a circuit, then you probably don't really care about the performance outside, or you only care insofar as you're going to be synthesizing a witness, in which case you're tied to the proof system anyway. But maybe there's other applications like where you want to be able to do like you want to have a signature algorithm that you want to just use as a signature algorithm, but then you want to be able to do stuff like produce a proof that I have verified a signature. Right. And so I don't know. I guess it depends.
I mean, you can convert between the two forms in the circuit.
I think there is possibly room to the thing that makes it expensive as you know, because you did all the analysis, is the sign checking, right? But if you had some different parameters, you might be able to write down like a more algebraic definition of negativity, and then you might be able to make the...
Let's get started.